Welcome back to another C++ tutorial video here on the Ludwig Fusel channel. In the last video we talked about if and else to basically control how our application flows. So in this case basically we scanned that x value and only if it was valid we executed print. So now today what do we want to do is we want to control how many times we do our computations. So let's get started by first adapting our functions so that we can control it. So first of all, let's start by adding a new parameter here in execute print, and I'm gonna call this count, and it's gonna be of type, actually, let's just keep it at int 32t count. All right, so this is basically what our count should be. Let's copy that count down to that function where it should be executed. But before we're gonna adapt this function, I just wanna simply adapt the code above here so that we can also use that count. So first of all, let's add another int32t. Now I'm gonna use that typo here and add the count. So what do I want to do? First I want to scan x, and scan x is now not really the one that we want to do. I want to rename this function just to scan int here as well, and instead of enter the value of x, I'm just gonna say enter an integer value. Right? It's not really descriptive, but it's at least telling us what we should do. So what I basically want to do is I want to have two results. Let's maybe call them R0 and R2. Maybe before I do this, let me quickly show you what I can actually do. Did I rename the function here? No, I didn't. Scan it. Okay. So one thing that you can do in Visual Studio is you can click on that variable, right click and click rename. And if I now rename this to R1 or R0 for the first result and click enter to preview that, it's going to basically check where this needs to be changed. So it's basically detecting it that it is checked in the if, it is checked in the else if, and it's used here on the name. And then I can hit apply and that's going to rename all of them right away. Just a bit easy. If you are doing this, it's automatically also renaming functions. If I rename a function, it's going to rename this everywhere as well. It's just a nice little helper. Alright, so now let's also create a result 1, which is going to be equal to scanning into count. Not scout, count. There we go. So now we have two results and we are scanning. So our condition that everything is good now needs to be expanded because result 1 also needs to be 1, and we also need to make sure that the result or that the count that was resulting from that read is bigger than 0, because the count needs to be bigger than 0. If it is not bigger than 0, then we have an issue. Right? That's understandable, I hope. And the only thing that's left to do is passing that count to the execute print here as well. Now, one thing that we need to do as well is we need to also check if the R0 was end of file or the R1 was end of file. So if one of them was an issue, we basically want to write IO error. Also, the inputs must be a number. They both need to be a number, just to make this sure. We have another condition that we need to input here. If count basically if R1 equals 1 and count smaller equals 0. So if the count is smaller equals 0, basically the user entered the right semantic value. So it's an int, but the int is invalid. And we're basically going to say printf the count second value needs to be bigger than 0. Just to have a bit more error checking in here. And if it would execute this, we can already check if our error checking is correct, if I wouldn't forget the semicolon. And then we can continue on adapting our function to actually reflect the count. So if I do this, still a bit of revisiting on booleans here, and an integer value, this is our x, let's put this to 5. Next integer value count at 2. Yeah, that's still its stuff, but it's correct. Now let's try adding 0 in both. The count second value needs to be bigger than 0. That's good. Let's maybe try a negative value, -5. Yeah, needs to be bigger than 0. Works as well. Now let's try an invalid value in the first value. It's already failing. So the second value is already failing. This is actually some behavior of C. The thing is, if it can't read the value that you entered, it is going to keep it. So basically it is the first time we are reading, it basically does not recognize this DFS as a number, and it basically keeps that for later. Then the second function comes in, it also can't read the DFS, but it's directly kind of like returning. It's not allowing you a second entering of the value because the DFSS was still stored in here, but the result that we get is the same. It's writing the inputs must be a number. It's a bit ugly, but we're going to get to that in the future, especially when we are transitioning to C++. We're going to talk about how to properly input something with C++ and do proper checking. And it's going to be a bit easier, especially with all of that formatting and outputting. So it at least works, yeah, right? If you're having the wrong value, it works. It's doing everything what it should. It's not particularly nice or pretty, but it's working, right? It's very simple to see what's going on and nice. So now let's try to adapt the function here. So previously we talked about if. Now you would be tempted to say if count smaller equal 4, for example, then I'm going to compute the 4 value and print the 4 value. And then I'm going to do the same for 3, and I'm going to terminate this, and yeah. But I basically, not a good idea. Not a good idea to check for each value here. Not a good idea to go from like 1, 1, 1, 1, 1 down to 1. Not good. So what we basically want to do today is basically we want to have an insert into t, I, which starts at maybe, let's say 0. And that I should go from 0 to count minus 1. And for every I, we basically want to compute that with I times x and that with I times x. So basically what we want to do is we want to count from 0 to count minus 1. And for each of these iterations that we count up, we want to do this computations. Now I'm going to show you 2 methods. The first one is probably the simplest one. So we want to do something while some condition is true. So while this I is going to be smaller than count, so from 0 to count minus 1. So while this I is smaller, I want to do some computations. What computations are we going to do? First of all, we're going to compute the y, and since we are now no longer storing this for each iteration, I want to say I times x equals y, and then I want to print this. I'm going to print again I times x and y, and after that, after we have done our computation, I want to increment I by putting this plus plus, which is again to revisit equal then root writing that. So nice while loop. Let's stripe this all away here, what we got here, and let's take a look at what we have done. So we have created a variable called I that's equal to 0, and while this variable I is smaller than count, so it starts at 0 and it counts to, in this case, 3, when we have 4 as an input, count 4, it counts to 3, and it executes for 0, 1, 2, and 3, so 4 times, doing its computations, printing, and incrementing. So it's counting up. So basically start value, condition, and step execution, incrementing each step. If we would run this, let's see what we get. So let's say the integer value is 5 and we want to do 4 computations. F from 0 equals 5, F from 5 equals 55, F from 10 equals 155, F from 15 equals 305. It's a bit different because previously we started at 5 directly, but I'm actually fine to start at 0. If you would want to start at 1 again, it's of course no problem. You can just say that you're starting at 1 and say smaller equal count. Now if I do this like that, we would have the same behavior that we have previously for the same values. For example, 5 and 4. It's now going to say 55, 155, 305, and 505. I mean, like 0 is really uninteresting because it's always going to be the same value. So we might just keep it here so that you can basically see what's going on. So you can see, yeah, very nice and simple looking. Can give any value like 4 and say 20 values, and I'm going to get 20 iterations of that application, and it's going to compute 20 values. Exactly how I want to do this. But there is one issue here, and I'm always a bit, I'm complaining much. It's a bit much code, right? We have like 1, 2, 3 lines for basically iterating over the numbers. 3 lines. I don't want to have that in 3 lines. This can be written shorter, or I want to write this shorter. And actually, since a while loop of that specific look is going to be there multiple times, you're always going to have while loops that look like that, where you have a variable that's initialized to a value, so something that's initialized before the computation starts, a iteration condition, so a condition how long this shall be running, and a step that needs to be executed after each processing. So a start computation, a start expression, a Boolean check, and a expression that is executed after each iteration of the while loop. A common form. We're going to have that all the time. And that is why we can write this in a single line. And now it's no longer be called while, it's going to be called for. And the for loop, by default, should look like something like that. That is how the for loop should look like. Just the thing that we do. No noise. No plus plus noise. No noise of initialization. No noise of checking in the loop. No noise, just plain. No noise above. No noise inside. Just noise inside the brackets. And how are we going to do this? Well, it's going to be the same that we have done here, but all inside the for. So the first thing that you enter in the for loop is basically the initial condition. This condition is terminated with a semicolon. The next thing that you're going to add is the check. So what it shall need to check to that. And the last thing, also separated with a semicolon, is the operation it shall do. Not terminated with a semicolon because we have the closing brackets. And that is exactly how a for loop works. This is done before the for loop starts. So basically what we have written above the while loop. So executed as the first thing. Then it's going to basically enter the while loop mode. It's going to check that condition. And while that condition is true, it is going to execute that code. And every time it finished executing that code, it's going to execute that expression, incrementing the I value. And then again, going into the check, if it's still true, executing that, incrementing the value here, or doing whatever you type in here. This is something that I see every time when I work with beginners in C or C++, that they are just using the for loop like that. But you can really write everything that what you want in there. The only constraint is that this is an expression, a C++ or C expression, later C++, now C, a C valid expression, like something that you could write in a line as well. Right? Something like that. Alright, I should just have pasted that down in here again, but yeah. So just a simple expression, Boolean check here, expression, only condition here. Can write everything in there, but just these three things need to match that for loop. So that basically has a initial expression, a condition, and a expression to increment. And of course you need to make sure that it is finishing some point. And if I do this like that, and press F5, we should get the same output that we had. Let's try this out again with 5 and 4, and we are getting exactly what we wanted. It's working, but it's way more compact and also easier to see. For that, do that. Not like while, and you need, if you have a big while loop, you don't need to scroll 5,000 lines down. You directly see that for loop, that signature, and see, all right, that is how that range of that loop is gonna go. I have an idea what it does, and then I can take a look at what's done inside of the loop. So way more readable, way shorter, and yeah, like everything, nice. So let's try this out again. Press F5, and maybe let's now go a bit mad so that you can see that you can also overwhelm your computer. Let's say maybe 5, and how many times do we want to execute this? Maybe let's say 90,000 times. And there is our computer crunching numbers and doing computations, and probably we are already getting overflows. This is why the values might get negative or 0. So basically the issue is that our value is so big that the actual range of a 32-bit number is no longer sufficient. And if it's not sufficient, it's basically cutting off values, it's cutting off bits. That's too much, and this basically means that at some point it is going to go to negative values. But you can see at some point it's actually finished. And I'm going to tell you something. If I just comment that out, you can create, I don't know, did I already told you how you can do comments? I think yes. If you comment this away by typing the double slash here, you can basically see that the application is going to be way faster. Like, what do we have? 50, 90, 1, 2, 3, 90,000, boom, already finished. So that is how fast your CPU is. The issue is that as soon as you are printing to the screen, you need to talk to the operating system. You basically need to tell the operating system, hey, I have the text that shall be written on the console. This needs to be synchronized to go to the operating system. Now the operating system is going to put this into a buffer. So a temporary location where it stores the text that you want to output. And it's going to wait until this buffer gets empty. And this buffer gets empty when another application of the operating system, so an application that was written for the operating system, is basically coming in It's actually the instance of that console. That instance of that console comes in and asks the operating system, hey, is there something in my buffer? Then the operating system says, yes, there's something in your buffer. This application takes it. The application needs to draw that. It needs to talk to the GPU and says, all right, I want to write some text there. And it needs to be all synchronized with the GPU, with the desktop, with the refresh rate of the monitor. And this is adding a so big overhead that, as you can see, the computation itself is fast, but printing this to the console is time consuming. Don't know how far can I go, like 9999999, something like that. Yeah, fast, done. We are on debug, which actually means that these computations are actually executed. On debug, we are enforced that it's executed. If we would switch this to release here, the compiler would take a look at this and say, what is that for bullshit? I am seeing a computation of y that is never gonna be used. Well, let's stripe this away. What is that for bullshit? A for loop that does nothing. Let's stripe it away. What is that for bullshit? A execute print that does nothing. Stripe that whole function away. What is that for bullshit? An if that is never executed. Stripe that away. And basically what you would end up if we compile this in release, you would end up with something like that. Because you don't do anything with the value you just computed, if the compiler aggressively optimizes stuff away. It could be that it doesn't catch all of that stuff that I showed you, but this is like the worst case that could happen. If you add the print, the compiler sees, okay, you are doing something, and even through a am on release, it's gonna do stuff, right? Because it shall do something. Just something that you should be in mind. If you're doing something in release that is really not a key, it might be optimized away. If I do this like that, for example, in release, and say, like 5 and 5, it does nothing. But the thing is, I might not be even able to reach the breakpoint. If I set the breakpoint here and click run, yeah, you can see that this breakpoint now gets this this warning symbol, and this warning symbol basically means that the breakpoint will not currently be hit because no executable code was generated, which basically means that there's no code. The compiler did actually stripe away that whole implementation. We can even try out if we get this here. No, it completely striped that away. If we take a look at the if, okay, the if is still checked here. So you can see it's good. It works. It's checking that if statement here, but it's not doing something. You can see all of these 3 breakpoints get the exclamation mark. So basically what the compiler did is it completely removed it. It's still doing these checkings because it only goes into the else if these checkings were not true. This is why it doesn't stripe the full if away. This is something that I have not thought of when I told this to you yet, because it still needs to make sure that this else is not fired if this condition is true. Because if this condition is true, we don't want to have this else fired. So basically what it does, it stripes that code away. It still does these checkings, and if these checkings are true, it's basically just returning the application. We could go even further, but this is for beginners probably a bit too hard. We can go into something called the disassembly. The disassembly is actually the binary code. We need to hit it actually. And if I now would go into this disassembly, we can actually see what it's doing. Okay, so this escalated quite quickly. What I can see here basically are the machine instructions that the CPU can execute. On the left, for example, you can see an address. That address is an address somewhere in memory, like where all of the data is stored. The stack is somewhere at an address which you could see on the left. All your dynamic data that we're gonna explore in the future, everything is gonna be at an address, which is represented here on the left, the hexadecimal number. And what also is stored there somewhere inside the memory is the actual application that you are executing. So when you write your C code and you feed it to the compiler outputs the machine code. And the machine code, of course, needs to be stored somewhere. When it's an exe file, it's stored on the disk. But as soon as you execute your application, as it starts up, it gets copied to the memory. So actually, your code gets a pointer as well. Your code gets memory addresses. Each of the lines you write become a memory address and are loaded somewhere into your memory for your application that you are executing. Now, when you are executing the application, you are basically telling the CPU or the operating system, Windows is going to tell the CPU at which location in memory the main function is located. So it's basically going to point the CPU to the main function, and then it's going to tell the CPU, go for it. So as soon as this go for it is kind of like reached, the CPU carefully takes a look at where the Windows operating system has pointed itself, and the CPU basically starts reading from top to bottom. So this you can see why this is like a listing. It's a listing from top to bottom. And then the CPU basically starts executing at the top and works itself down to the bottom and does everything that is in here. For all of our if and else operations, there are so-called jumps. Jumps are basically telling that CPU to go somewhere else, to another address. And that address where it's going to is, of course, an address inside of our binary application code. So it basically jumps for the execution, jumps to that other address and starts reading code from there. So what you can basically see here on this view is on the left is the address, so basically the address where the code is stored. On the right you can basically see the actual instruction that the CPU should execute it. These are hardware instructions. This is actually what the CPU can do. These are specialized hardware functionalities built into silicon. So for example, adding values together, subtracting values, jumping if a certain value was 0, for example, doing some comparison. All of these are hardware built-in functionalities that the CPU can do, and they all have a name, and that's basically what I see here. This part of the video is completely optional. I would highly recommend taking a look at this, but it is more complicated than what else would we ever have done. Because programming already, especially in C and C++, is already quite complicated, and here we are giving another thing on top of that. We are basically now taking away all control structures that we have in C and C++. So all of the variables, all of the if, else, assignments, operators, plus, minus, they are all non-existent in assembler code and machine instructions. And basically what you see here are the raw machine instructions. I'm gonna try to walk you through that piece as good as possible so that you don't need that many actually, you don't need any prerequisites at all. I'm going to explain everything, but if you are struggling with that, it's not a big deal. You can rewatch it later. It's just some nice facts that you might want to take a look at. But it's not 100% critical that you understand this part. So, now, continue with the video. And if I now would go into this disassembly, we can actually see what it's doing, and you can actually see that it is currently inside of these if checkings here. And what this is checkings basically do here is doing some shit at, and here it is basically exiting the application. This jump, this GMP to that one is the exit of the application. So this is basically, if this condition is true, it is basically doing multiple things. It is checking three things here. And this is basically checking the first thing, it is going out here, it is checking that thing, going out here, it is checking that, it's going out here. Maybe these are ordered a different way. And basically what it is doing here, the last step is basically if this condition is true. This is the last thing that it's doing here. And as you can see, it is basically the last thing because it's directly above the text output of our code. And what it's basically doing, it is going to main, our main function, plus 97H. We could try and actually compute this, where this is. So if I go a bit up, you can see this is our main, and this is the value of our main. So can I copy this? Let's try this out. Let's open up the calculator. Make sure it is on programmer mode, and it's set to hexadecimal, and now I can paste this value in that I just copied from here. And now basically, where are we going? We are going to main plus 97 hexadecimal. So plus, still make sure that you are in hex, 97, enter. Now we are getting this value, 177. Is it still at? Yeah, probably. So the 1177. Now let's scroll a bit around and find that 1177. And if I scroll a bit around and find that where is it? 1177. You can actually see that this is already behind that closing bracket. So you can see down here, there's again this call printf, which is basically calling the function printf, and this is the last printf that we have written in our application, which was printing the IO error. And if you take a look at this, IO error was the last real expression that we have done in our application, so the last thing that is stored inside of the main. And what we are doing, we are directly going to that call after that printf, so directly to this XOR, whatever this is doing. I know what this is doing, but it is basically the thing that is doing some cleanup for that main function. So basically, this whole expressions are cleanup procedures that are being introduced by the compiler that basically makes sure that you are safely going out of the main. And then down we are going to ret, which means return, and it's basically now returning out of the main after it did all that cleanup, and we basically came directly above from this checks, and this basically means that the whole call of our function, or basically the full execution of that statement, has been striped away by the compiler because we were doing nothing. And this is why C++ is so powerful, because the compiler does amazing things like that. Why should we override 999,000 times, potentially, over some code that is not executed? So the compiler does think for you. If I would now stop this and go back to debug, it would be looking quite differently. So you can see that the breakpoints are there, and that actually now this jump that we had previously to the, what was it, 7.9, I think? Yeah, 9.7. The 9.7 jump is no longer in here. So if all these checks that we're basically checking if these conditions were false, so if one of these conditions was false, and we are basically jumping over that, as you can see, now we are always also jumping to 6.5.h at this bad value that you don't like. This is something that is also there because of debugging. But basically what this jump means, jump to that. Here, to that, no, not to that, to that expression here, to this one here, which is also jumping around, but not really the thing that you should be concerned of. So basically, what was going on here is we no longer jump away. You can basically see that we are going down the rabbit hole and we are calling execute print. So call execute print means call that function. We don't go away if that condition is true. We call that function anyways. And if I would go down to that, I can actually copy this and paste that down here. I could also copy that execute print and write it down in here. And now you can basically see we are at C, user tutorial, simple C app, and now we are at execute print. We can see what execute print does, and you can actually see that this is our for loop that has been executed. So this whole code is for our for loop. Again, you really don't need to understand this as a beginner, what's going on here. In the future, we're gonna might potentially take a more look about this disassembly here. This is actually the instructions here that the computer does. Something that I might should have said when I started this, but I'm probably going to edit this, so that is not going to be an issue. So here looking at the instructions that the machine is actually doing. This is the fundamental operations that the computer does. And this code is basically just for the header of our for. This is basically initializing the value, probably, initializing the value to 1 here. For example, this is a 1, and this basically stores it where it needs to go. Then it basically goes to execute print plus 33h, and 33h is basically that expression, so it starts the operation, initialize the value, starts the operation. Then basically that one here is our increment step. Basically here you can see that it is doing stuff. It's basically loading the value of our I. So this is basically our I, this RBP plus 4 is our I, and basically what it is doing, it is storing at this position of our I, it's storing the 1. Here it's basically loading this 1, or that I, which is currently a 1. Then it's gonna increment that 1, this is inc, means increment the value stored in EAX. EAX is basically where we temporarily stored our 1 in this case, so we basically put in our 1 to EAX, loaded this from the I location, loaded the I, stored it in EAX, incremented this I, stored in EAX, then we move it back to where we stored it previously, to EAX, and then we are actually loading our count. After we loaded our count, we're gonna compare it to our I value, and if that comparison did not succeed, we're gonna jump out of that. There, go out of the code. If it was successful, we just continue down here, which is basically what we are doing in our for loop, which is loading the I, multiplying it with the X, moving it to some other location, and then calling the function f. Then it's doing some more moves. This move is basically moving the return value from the f to the storage of our y here. And then if we are down here, we are gonna jump. And when we're gonna jump up to that incrementation step. We're gonna increment here. Then we're gonna compare again, and if the comparison results, we basically go out. We are doing some cleanup here with Lea, pop, and we are returning back to our main function. I hope this was not too much, but I think you have enough knowledge to understand it already. If you didn't understand it, not a big deal. You're gonna probably understand it later in the future, but I think it's important that I show you stuff like that to actually see what's going on, because like C is just text. It is just text, and it needs to be transferred to something meaningful for the computer. And the text, the computer doesn't understand it, but everything which has like this address before it, this is what the computer understands. You don't need to understand it step by step. I tell you something, I don't understand it step by step as well. I know simple operations like these, but there are more things that are doing here. So like call, this one, call, check for debug, just my code. This is some debug stuff that's going on. Here are some initializations. I cannot really tell you out of my mind. I can take a look at this, what all this means. And I know what it means, but I cannot tell it. I don't know it that much that I can tell it to you, just out of my mind. If I look it up, it's no problem, but yeah. Doing some stuff around there, basically. And if we are on debug, we are getting what we see. If we are doing debug, we get what we see. If we are doing release, we don't get what you see. This is like the main takeaway here, which like escalated very quickly into disassembly, but yeah, let's close it up. This is for a while, but I think it's okay because this video would be quite short if it wouldn't be that long, which is like simple, but yeah. That's it basically. Not gonna bother you anymore with that stuff. Was enough for today. So thank you for watching. Hope you enjoyed it, even though it was a bit more complicated today, but the main takeaway, for and while loops. Thank you for watching. See you in the next one. Make sure to like and subscribe, and have a nice day. Bye.